Okay, here's the third in the series of 3, Physics, GCSE for AQA. The third topic is nuclear physics, the shorter one of the 3, and it's all about the nucleus of an atom. Until 100 years ago, people thought that the atom was a bit like a pudding. They called it a plum pudding at the time, and it was made up, it's like a sphere, like a circle or a ball, with charges dotted around inside of it. And everybody thought this was a good model of what the atom actually looked like. Then came along Ernest Rutherford, exactly 100 years ago. He did an experiment with a few assistants, and he discovered and shattered this structure of the atom and came up with a different one. This is what he did. He fired alpha particles at a thin gold leaf foil. So here's what he thought the gold leaf foil looked like, according to the plum pudding model. He got alpha particles which, on this is not to scale, are much, much smaller and made up of 2 protons and 2 neutrons, and he bombarded the thin gold with the alpha particles, and he observed it. He observed thousands and thousands of these particles, and you can see as they go through, most of them actually go through the gold foil. They actually pass straight through. Then every now and again, you'll find that one of them might be deflected. So if you watch this one, it'll be deflected backwards. What does this mean? It means that the path of the alpha particles themselves look a little bit like this, where most of them go through the thin foil and only 1 or 2 come back. In fact, what he concluded was only about 1 in 8,000 came back, bounced back, where really the plum pudding model you would expect them all to bounce back. A bit like firing tennis balls at a wall, you'd expect them all to bounce back off this solid. So the conclusion here, what Ernest Rutherford came up with, very important discovery, is that the atom is actually made up of small positively charged nuclei, shown here red dots, and the gap between them is mainly space. So the alpha particles can actually just go straight through them because there's nothing to stop them. And he showed that these atoms, the nuclei of the atom, is very, very small compared to the space between them because of them going through. So Rutherford came up with this structure of the atom, very much like the solar system, where in the middle you've got the nucleus, which is made up of protons and neutrons. So that's compared to like our sun. And around the outside, orbiting them, is the electrons. And the space between the electrons and the protons is massive. So it's a bit like our sun in the middle with the planets orbiting around. You can imagine most of it is actually space. And this is the solar system model, if you like, of the atom that you'll be familiar with. So the atom is made up of protons, neutrons, and electrons. Remember that protons, P, standing for protons, is a positive charge, and electrons are equal and opposite minus charge, and neutrons have a neutral charge. And in terms of mass, the protons and neutrons carry all the mass, and they have equal mass, so we call the relative mass 1. An electron has such a small mass that we can consider that to be 0 compared to protons and neutrons. We can represent atoms in a periodic table like this, where you've got the top is the mass number, so that's adding how many protons and how many neutrons there are. So in this case, 4 means that there are a total of 4 protons plus neutrons, so it's 2 of each. And the bottom number shows the proton number. So for helium, there are 2. We know it's helium because the symbol He is represented there. So there's 2 protons, so there must be 2 neutrons. Some atoms can exist in different forms. So for example here, we have oxygen. We have 3 different isotopes. Isotopes mean different types of the same element. We know it's oxygen because it has 8 protons, but the mass can vary. So if you look at this, we can have a look at the different masses. So it's oxygen. Oxygen must have 8 protons, otherwise it would be a different element. For this one, you can see that 8 and 8 would add up to 16. So there must be 8 neutrons there to give a mass of 16. Whereas this isotope of oxygen has a mass of 17. It means it must have 9 neutrons because it's got 9 protons. Sorry, it's got 8 protons, so 9 plus 8 is 17 mass. And this one finally would have 10 neutrons, so 10 and 8 protons would add up to a mass of 18. So these type of isotopes are also called radioisotopes. Radioisotopes means that they're radioactive. Means that this oxygen and this oxygen isn't stable or as stable as this, so you'll get some sort of decay, radioactive decay. we get naturally occurring decay from all around us. About 50% of our background radiation in the background, is from radon gas, which is naturally occurring. And we get a small percentage from food, because the food is grown in the ground, or animals eat the food, which have got radiation in the ground. We get a small percentage from cosmic rays and also from gamma rays from outer space. And we get an amount from medical and also from nuclear power. These two are the man-made ones. They're the ones that we actually make. But that only constitutes about 13%. In a whole, the most of it, or 50%, is radon gas, which comes from naturally occurring radioactive rocks in the ground. 3 types of radiation. In detail, the first type of radiation you can have is called alpha. Alpha is the first letter in the Greek alphabet for A. An alpha particle is 2 protons and 2 neutrons, so it's the same as a helium nucleus. So if you look at this unstable nucleus, might break away 2 protons, 2 neutrons, so this new nucleus has 2 protons, 2 neutrons less, and therefore you get what's called an alpha particle. The second one, obviously the second letter of the alphabet, the Greek alphabet, is beta. And this is a bit more complicated. You can see that this neutron here can actually turn into a proton. So the neutrons are coloured green. They're not really green, but just to represent here they are. It can turn into a proton. When that happens, an electron is emitted. And this electron is called a beta particle. So quite complicated. Beta is when it decays by changing a neutron into a proton, and then an electron flies off. This fast-moving electron is called a beta particle. And the third type, the third letter in the Greek alphabet, is gamma. Gamma is not a particle. Gamma is a wave, and this is what you get off when one of the others happens. So gamma is, after alpha beta happens, you get a packet of energy called gamma rays. Gamma rays, you'll remember, has the highest frequency with electromagnetic waves, and it gives a very short wavelength. And the atom is not changed when gamma rays come off because it's not a particle. The amount of energy we can get from the nucleus is massive. And there's 2 ways we can get energy from the nucleus. The first one is nuclear fission. Nuclear fission means to split the atom, to split the nucleus. And the way to do that is to bombard an atom, a very large atom, for example, uranium, with a neutron. So uranium or plutonium are the nuclear fuels that's used in the nuclear industry. Very large atoms that can be split. So if you bombard a nucleus of uranium with a neutron, what you'll see happen is the uranium will split in 2. And when this happens, when it splits in 2, you get a lot of energy off. And this energy is created and given off. Very, very large amount of energy. But what also happens is you get another 3 neutrons coming off. So you put 1 neutron in to split it. You've got the 2 new nuclei, which will be not uranium anymore. In this case, it's barium and krypton. 2 new nuclei. But you get 3 more neutrons coming off. And remember, this gives a lot of energy. If you then follow that through those more neutrons, you get something called a chain reaction. A chain reaction, let me describe it here. So here's a neutron coming in. Neutron splits the atom in 2, giving off a lot of energy, and also giving off 3 new neutrons. Now, if those 3 neutrons go off to collide with 3 new uranium or plutonium nuclei, then you will get 3 more reactions, 3 more splitting of the nucleus, and there are 3 more reactions giving off 3 times the energy. And if you follow the logic through there, we'll get another 3, 3, and 3, so another 9 neutrons, which can cause that. This is called a chain reaction, and this is how nuclear disasters can happen if it gets out of control, but it can give off so much energy. The other type of nuclear energy can be from fusion. So fission was about splitting the atom. Fusion is about joining or fusing nuclei together. This is what happens in the sun, in our sun and other stars. So this is what happens. 2 protons can join together, quite complicated, but can join together with neutrons until you get a helium nucleus. And again, you get off a lot of energy, and you've got this alpha particle here, which is a helium nucleus, and 2 more protons which will go ahead to join together and form more helium. So stars is a nuclear fusion reactor, if you like, where protons, which are hydrogen, is turned into helium. When hydrogen is turned into helium in this process, nuclear fusion, you get a lot of energy. So our sun has been a nuclear fusion reactor for thousands and thousands of years, giving us all this energy. Eventually, all of the hydrogen will turn into helium. It will therefore run out of fuel and eventually die. But that's many, many thousands of years to come.